All right, everyone, welcome and thank you for joining us. This is our final project. This is the team still in progress, but it'll do.
And this is Will Pacheco and Robbie Stoll. To start, we wanted to go over some of the data listed here for our project. We combined 5 data sets to pull in the emission, biomass, total wood removal from forests, and total landmass from forests, so that we could compare the data and answer some additional problems here in addition to some research questions on our next page.
Okay, so on this page right here, you have 4 different variables to choose from, change the different x-axis. And so what we want to look at is, are these things increasing or decreasing in the United States? And as you click through each indicator, you'll see the trend line that will tell you different information about each one. And this is just for the United States. You can see positive trend lines right there for land mass. Decreasing trend line over the past about 7 years here for removal. Biomass increasing. And CO2 emissions has actually been decreasing in the United States over the last about 6 years or so.
Now, the second plot here, we actually compare a couple different things. We compare how biomass is affected by CO2 and forest wood removal. Then we also compare wood removal to forest land mass to allow ourselves to see a trend there. So the first two, we see emissions compared to biomass, with biomass being your x-axis. As the biomass increases, we see a jump in emissions. This is human emission, though, so it's not like this is atmospheric composition. But the emission level increases, but then it decreases fairly rapidly. If we compare biomass to wood removal, there is a slow decline as biomass increases. And then comparing forest wood removal to forest land mass, obviously the more land mass there is, the less wood removal we end up seeing. So those two kind of go hand in hand.
Transition next to our page 2 static analysis. This is really the section where we start to go over our research questions and show the summaries and a lot of the data for our exploratory data analysis.
Now we come up with 2 research questions for this data. The first one, does CO2 emission positively affect biomass and forest coverage? And then does forest wood removal negatively affect CO2 emission, biomass, and forest coverage? And this table that we see here is the average summary by continent for each of those. So we see
average emissions, average biomass, average forest coverage, and average wood removal.
And we see the actual units for tons per person for emission, tons per biomass,
and the hectares,
forest coverage. And this one actually I messed up in typing that out. Cubic meters for wood removal and tons per person for emissions here. Biomass is tons as well. Now, going down to correlation values, we have, with our first one, emission versus biomass. With this, we have 0.02, fairly low, well, really low, and actually a lot lower than we expected, considering emissions and carbon dioxide highly affects biomass in general, but this, again, is human emission, not just total atmospheric composition, so I guess that kind of makes sense. For emission versus forest land mass, we have a still fairly low correlation value. So this is saying that the human CO2 emission doesn't affect forest land mass as much as we'd expect it to. For biomass versus forest removal, this one actually did have a fairly high correlation coefficient. So it kind of makes sense, because the more biomass, or the density of biomass with the amount of forest removal, would obviously make sense. And then the forest land mass versus wood removal had an even higher correlation coefficient, because you remove more wood, you have less forest. Going down
through our plots, it shows our different continents, and each of the dots shows actually the amount of biomass in each continent. So this is really useful because we're using these indicators for our models that we're doing for different regression modeling, and then when we talk down to the other sort of speculative and predictive models that we do later on in this study.
So here we've actually created a couple linear models or regression models. The top one is a multiple regression model that includes biomass, emission, removal, and year. The second, third, and fourth one are individual regression models. So it takes those same values, biomass versus removal, biomass versus year, all of that, and it separates them into their own models, slightly different than the total, but we're going to use the total for this purpose. We created those other additional ones so that we can create AIC and BIC models or values, which we'll go over later. But at this point, we want to explain what we see in our multiple regression model that compares all of these values. So with this, the first thing we wanted to do is determine significance in our models. So to do that, the first thing we're going to do is check the p-values for each of our models here in the total, which we see is right here.
Remember, it is significant if it's below 0.05 for the p-value. And here what we're seeing is a very, very small 0.16 zeros, 0.22, so a very, very small number.
And definitely significant. For each of the individual ones, we see something interesting, though, because we have 0.09 for emission, again, another 16 zeros after a decimal and then 2. So this one obviously is significant. These two are not, though, as they are higher than 0.05. After we've gone over our p-values, we also have the t-value to signify significance as well.
For the CO2, the t-value is negative, but it is still close to 0, so the observations are still less recognized in the null hypothesis and add to the data significance. Wood removal, as the t-value for forest wood removal is high, it means you would normally see these observations in the null hypothesis, making the information very much less significant. For the year's t-value is very low, adding more significance to this data than the other two observation data sets.
Next, the thing we want to analyze is the R-square and the adjusted R-square value. So for our data, or our table here, our linear model here, the R-square value for our multiple regression model has fairly low, meaning that there's less variety in our data, which would allow us to create prediction models a lot more accurately. The adjusted square value is also fairly low, signifying our ability to create more accurate prediction models as well.
Yeah, and when we keep carrying on down, we do analyze our standard error, which is really our goodness or fit, to the extent of which the data observes matches the values in the prediction. So for emissions, the standard error shows that our model to have not the best fit, making our predictions less accurate. When we're looking at removal, as this is a fairly high, but not exceptionally high, we can see that they're fairly accurate predictions that fit the current status of our model. And it should be pretty reliable. For the year, this is incredibly high, meaning that we can predict with precision using this model.
All right, then last on this list is going to be our F-stat. With this, we see that it's fairly high, and also, or with our
it really shows reliability in the prediction modeling based on the number being slightly higher within in the degrees of freedom set by our prediction model.
Now, after we have this information, the final thing we wanted to do to see whether or not our information could be used for predicting would be to come down here to create a comparison of the AIC and the BIC. Now, that's going to be a Kayak's information criterion and the Bayesian information criterion. And with these, the lower the number, the better to determine whether or not we can use these for predictions, or at least to determine which would be a better fit for predictions. So were we to consider all of the 4 models we have, our inclusive model having the lowest numbers would be the most prominent and the one we'd want to use.
Just to quickly touch on what each one of these are, our individual model 1 is biomass and emissions comparatively. Our individual model 2 is biomass versus removal comparatively. And our individual model 3 is biomass versus the year.
Now, out of individual models, if we were to pick just these and exclude the inclusive model, model 2, which would be the wood removal comparison, would be the one that we would select as being the most accurate using these 2 methods for prediction analysis. Now, in summary, we wanted to go and answer our questions. Does CO2 emission tons per person positively affect biomass in tons and forest coverage in hectares? So with this, from our data, we can accurately recognize the positive effects of CO2 on biomass and forest coverage, though through different degrees with additional observations are applied. Additionally, as expected, forest wood removal does negatively affect CO2 emission, biomass, and forest coverage, but again, this is in various degrees with additional external factors not included in our data set.
And in conclusion, we just want to thank you for powering through that our presentation with us, and I hope you enjoyed it. And this is where we'll open up for questions. So thank you.